Hello everyone, and welcome to my channel. This channel is for educational purposes, and we look at various theories of everything. So far we've done deep dives on the ancient Egyptian tree of life, and today is our 464th video on the reciprocal system of theory originated by Dewey B. Larson. Mr. Larson was an engineer in the 20th century in the United States. And, excuse me, he proposed his two fundamental postulates around 1959. And these two postulates explained how the universe operated. In short, they are, the first postulate is that the universe conforms, no, the universe is composed entirely of one component, motion, existing in 3 dimensions, in discrete units, and with 2 reciprocal aspects, space and time. The second postulate is that the universe conforms to the relations of ordinary commutative mathematics. Its primary magnitudes are absolute, and its geometry is Euclidean. So Larson took those 2 postulates, and from them he derived a theoretical universe. Basically, what his universe would look like if his postulates were correct. And he compared his universe with the universe that was measured and compiled in tables by all the legacy scientists of the past, how many ever years. And we're looking at the results of one of those studies right here, a book called Basic Properties of Matter, that's on chemistry primarily. And we are in chapter 7 on temperature relations. Now let me just elaborate on Larson's first postulate. The second postulate is basically, axiomatic for scientists. We use math, we use logic, we use geometry to figure these things out. Now, he specified certain kinds of math and geometry, and other people have disagreed with those. I don't really even think that was Larson's point, to describe what kind of math or what kind of geometry we're going to be using, but more that that's how we're going to determine this. You can see this in this chapter here, chapter 7, where he talks about the probability functions. There are many different kinds of probability functions, but in the, at least in the first analysis, he doesn't really care which one he uses, because it's kind of like splitting hairs. All he's really saying is that the universe conforms to the relations of probability. Some of these different probability relations are very similar to one another, and he chooses one. I mean, there's a bell curve, and then there's various offshoots of that. He just chooses the normal probability function, and the universe conforms to that. And it may conform slightly more to a different probability function, but the results of the laboratory experiments that the legacy scientists have done aren't even accurate enough to justify really figuring out which one is the most accurate. Okay, so the first postulate is where the main content of Larson's reciprocal system is. The universe conforms to the relations. No, sorry, again, the universe is composed entirely of motion. Motion exists in 3 dimensions. It exists in discrete units. And it has 2 reciprocal aspects, space and time. Now, when Larson isn't the first person that's attempted to construct their universe upon motion, like as opposed to matter or energy. But Larson was successful, I believe, in making a full general theory out of matter, out of motion, because he defined motion as the relationship between space and time. That implies a reciprocal relationship between space and time. Motion is a fraction, with space or time as the numerator and time or space as the denominator. And you can see that in the most basic kind of motion, speed. The bike is going 10 miles per hour, 10 miles of space in 1 hour of time. Space over time. Speed is space over time. You see the reciprocal relationship. If you double the speed, you can then say the bike is now going 20 miles per hour. Or equivalently, you can say the bike is now going 10 miles per half hour. Either one works. Multiply the space by 2 or divide the time by 2 in this case. And that shows that there is a reciprocal relationship between space and time. Now, what Larson does is he extrapolates that speed relation to all other kinds of motion, really all kinds of scientific phenomena or events, that they are all motion. Matter is a motion. Energy is a kind of motion. Pressure is a kind of motion. Acceleration is a kind of motion. Force is a kind of motion. Electrical resistance is a kind of motion. Magnetic permeability is a kind of motion. And they all have their space-time signatures. Matter is time to the 3rd power over space to the 3rd power. Remembering that, motion is made out of space and time. Space and time do not exist other than together in motion. So motion is made out of space and time. Motion has 3 dimensions. Space and time have 3 dimensions. So you can go matter is time to the 3rd power over space to the 3rd power. Energy is just time over space. Pressure is time over space to the 4th power. And so on and so forth. And this is a system of using units that is more effective than the MKS system because you're getting rid of the mass quantity. You're not using meter, kilogram, seconds. You're just using meters and seconds. And you've converted the kilogram part to time to the 3rd power over space to the 3rd power. Or, seconds to the 3rd power over meters to the 3rd power. And so that serves as a good check. But then you also have, you've got your 3-dimensionality of space. Larson calls that coordinate space. This is the space that's right in front of our face. And 3 dimensions, XYZ coordinates, up, down, back, right, back, forward, left, right, and in a still frame. But we also perceive time to be progressing in a scalar manner. Time is always getting later and later and later, but in no specific direction. Now, I don't believe I mentioned scalar motion. Now, when Larson talks about motion, he's really talking about a more generalized kind of motion that he calls a scalar motion. A scalar motion is a motion that has a magnitude, but it has no specific direction. A scalar motion has been recognized by science, but has been kind of ignored in its importance. They recognize that it exists, but they think it's kind of irrelevant. But Larson puts it at the very center of his reciprocal system. You can envision a scalar motion using a balloon with dots on it. If you blow up the balloon, all the dots will be moving away from each other. That is an outward scalar motion. Larson calls it a progression. And the dots are all moving away from each other, but in no specific direction, or really in every direction. Every dot is moving away from every other dot. And really every location on the surface of that balloon is moving away from every location. Every point on every location on the dot is moving in every direction. So there is no specific direction. If you deflate the balloon and contract it, all of the dots will be moving toward each other. And Larson refers to this as gravitation. So really that outward motion, the progression, is an omnipresent, eternal motion. This is, in a universe of motion, you have to be able to accept the concept of motion without anything moving. And what you really have here is you have the progression of time and the progression of space at all times, in all places. It's really kind of like an internal progression. It's not that we're expanding in space or we're expanding in time. It's that time itself and space itself are expanding. And we are along for the ride. And that's really the source, is this progression. Now, the source has to be harnessed in order to start a universe of something, as opposed to nothing. When you have nothing, you just have this outward motion. But when you have something, you're basically turning that progression into gravitation, turning that outward motion of the balloon to an inward motion. And you basically do this through first a vibration, which reverses that outward motion, which will reverse the outward motion in either time or space, while the other one continues to progress. And that's called a photon. And then that photon needs to be rotated in 3 dimensions. Again, the universe is 3-dimensional. So that photon has to be rotated. There's a few other complicating factors, like you have to put another photon in there. So really, like 2 photons will be rotated in 1 dimension, and then they'll combine. They'll need to add another dimension again, but basically the photon has to be rotated in 3 dimensions for it to begin to gravitate. And so that gravitational motion is inherent to the matter, to matter. And that's Larson's periodic table, is based on 3 separate rotational motions, 2 of them in 2 dimensions and 1 of them in 1 dimension. And those are the numbers that Larson uses to determine many of these basic properties of matter that we're going to be talking about. And this also really answers the question of gravitation. It's been a question and a conundrum for legacy scientists forever about gravity. What is the speed of gravity? How does it propagate instantaneously, all the way across space? Where is the force, the action at a distance that is occurring? How does that occur instantaneously? Well, the answer is that it's not. The answer is that gravity is inherent to the body, the matter, and it doesn't have anything to do with any other bodies. There is no force. You can see that in an inward scalar motion. Each one of the dots is pursuing its own course, but they're all moving toward each other. They're all on a contracting space. So they are all moving toward each other. There is no force between one and the other. You can kind of create a force between one and another if you decide to assign one as the reference point and say that this particular dot is motionless. If you do that, then it appears as if all of the other dots are moving toward your dot and your reference dot, and that there is a force field emanating from your reference dot that is attracting or repelling all these other dots. But that, and you can use the same math, but that's not what's going on. Each dot is pursuing its own course, and that is why there is no propagation of the force, and so there doesn't need to be any time involved. And so you have this gravitational force, or as if force is what Larson calls it. This gravitation that's inherent to the matter. And when you are in a gravitationally bound system, then you experience this 3 dimensions of space in a still frame background, along with your progressing time. Time is still moving in a scalar manner, but space has become stationary. Now, there is another place in the universe where the opposite would be true, or the reciprocal would be true, because of the reciprocal relationship between space and time. There's another place in the universe where time would be stationary and 3-dimensional, while space would be progressing. Everything would be getting farther and farther and farther apart. And time would be 3-dimensional with XYZ-like coordinates. Not XYZ, but like XYZ coordinates. And so Larson refers to these 2 reciprocal things as the spatial reference system and the temporal reference system. And these are both stationary reference systems. But then Larson also has the natural reference system. And the natural reference system is the progression. And, Larson has this discrete unit postulate. Motion, space, and time come only in discrete units. And the rate of the progression is, or the speed of the progression, is 1 unit of space per 1 unit of time. Space over time is speed. 1 unit of space per 1 unit of time. That is the speed of the progression. And that occurs at all times, in all places, eternally. And that is what Larson calls unit speed. And it turns out that that is the speed of light. So the speed of light outward in all directions is the empty universe, and it's what Larson calls the progression of the natural reference system. So Larson makes his measurements from the natural reference system, whereas legacy science makes their measurements from the stationary spatial reference system. And so there's distortions involved in having made that abstraction. And that is why scientists can't figure out what's going on, because they're not measuring from the right reference system. They're not measuring from the actual reference system that scientists are using. Now, in my mind, as an aside, it turns out that Larson didn't quite go far enough. And if he would have been reading his contemporary Buckminster Fuller, he would have also recognized that as a geometrical matter, he is not using the reference system that nature is using either. And he needed to change that reference system to the synergetic geometry reference system of Fuller, where it's based on tetrahedrons, triangles and tetrahedrons, as opposed to squares and cubes. And so if Larson would have made that other adjustment, I think it would have made things easier for him. But as it was, the natural reference system is a great improvement. Now, so basically, you have this progression at the speed of light in all directions. This is the midpoint or the null point or the state of rest of the universe. Half the universe is moving faster, half is moving slower. The half that's moving faster is basically unknown to so-called science. That's called the cosmic sector. And the other half, the slower than the speed of light, which we are familiar with, is the material sector. In the material sector, you have the spatial reference system. In the cosmic sector, you have the temporal reference system. And within each of those sectors is a subunit where you have less than 1 unit of space in the material sector and less than 1 unit of time in the cosmic sector. This is the realm of atoms and molecules interacting. Larson refers to the material sector as subregion as the time region, and the cosmic sector subregion as the space region. And in those sectors, the rules are different. They reverse. And because you can't move in space, there's no such thing as less than 1 unit of space, so everything is in time. And when you look into that sector, you have to take some things into account, like what he calls the interregional ratio, and also the fact that he calls it equivalent space. We don't see time. We only see space. So things are occurring in time, but we see them in space. But we see equivalent space. So Larson calls it equivalent space, and we see equivalent space as a second power function. So we have to take that into account, and then there's also something that's lost in the translation when we look into another region or another sector of the universe. And so that also has to be taken into account. Also, the progression and gravitation change their direction at that unit speed, unit space, or unit time boundary. And now the progression is inward in equivalent space, and gravitation is outward. Now, pertinent to the progression would be compression, and pertinent to the gravitation would be heat. And so that is really where Larson starts his probing here in his book, Basic Properties of Matter. And we're looking at his 3rd chapter out of 4 on temperature. And this one is called Temperature Relations. And we'll just start here and we'll see, how many lacuna Larson gets into that I have to try to explain his way out of. He's in the weeds a little bit with a lot of detail that you probably don't need to know yet. But there's also a lot of little breadcrumbs that you can pick up when you read Larson. And you have to keep in mind that this is a generalized theory. So even though we're reading about chemistry, what he's talking about applies to all fields. Even though you may not quite see how to be able to apply it to all fields yet. But it is a generalized theory. So you're not just learning something that only has to do with chemistry. It has a wide application. Okay, so this same restriction to one of a limited set of values also applies to the temperature of the solid molecule. But in the vicinity of the melting point, the solid is at a high time region temperature level, where the proportionate change from one possible value, n units, to the next, n plus 1 units, is small. The motion of the liquid state, on the other hand, is in the region outside unit space, in the material sector, what he calls the time-space region. But that's just in one dimension. Because a solid is in the time region in 3 dimensions, a liquid escapes from the time region in just 1 dimension. So it's got one dimension in the time-space region and two dimensions still in the time region. A gas is where you have all three dimensions in the time-space region. And okay, so the motion of the liquid state, on the other hand, is in the region outside unit space and is equivalent to gas motion in the one dimension in which the thermal energy exceeds the solid state limit. As we saw in Chapter 5, temperatures in the vicinity of the melting point are very low on the scale applicable to this outside region, and the proportionate change from n to n plus 1 is large. The intervals between the possible values of liquid molecules are therefore large enough to be significant. Again, the point that he was making yesterday is that temperature is not continuous, because temperature is on a molecule by molecule basis, and it has certain, everything in the reciprocal system is quantized, the discrete unit postulate. There are units, and so every atom, when it moves up in temperature, it moves up by steps, not like in a continuous manner. But we see it as continuous because we only see aggregates of matter. So we see bazillions of atoms, and they're all averaged together. But when you really break it down to the quanta, then you see that each molecule has its own temperature and it has its own state of matter. And so an aggregate may have 20% of its atoms are liquid and the other 80% are solid. We would still see the aggregate as solid. And Larson apparently, not theoretically, but empirically, says that approximately 30% of the molecules need to be liquid before the aggregate is perceived as being liquid. I guess that 30% is enough to kind of like break the geometrical bonding or the crystal structure bonding of the solid state, and now it's in more of a fluid configuration. Okay, so because of the limitation of the liquid temperatures to specific values, different levels, the temperature at which a molecule qualifies as a liquid is not the endpoint temperature of the solid state, but a higher value that includes the increment necessary to bring the endpoint temperature up to the next available liquid level. So that would be the initial point of the liquid, is a little bit beyond the solid state up to the next level. So the solid state might end here, and you can theoretically turn into a liquid here, but you have to get up to that first level. This makes it impossible to calculate melting points from solid state theory alone. Such calculations, so you can calculate this end of the solid, but you can't quite calculate the melting point just from the solid. You have to understand something about the liquid. So such calculations will have to wait until the relevant liquid theory is developed in a subsequent volume of this series or elsewhere. But the temperature increment beyond the solid endpoint is small compared to the endpoint temperature itself, and the endpoint is not much below the melting point. A few comparisons of endpoint and melting point temperatures will therefore serve to confirm in a general way the theoretical deductions as to the relations between these two magnitudes. There is a considerable degree of uncertainty in the experimental results at the high temperatures reached by the melting points of many of the elements, and there are also some theoretical aspects of the thermal situation in the vicinity of the melting point that have not yet been fully explored. Now, keep in mind that this book was written in 1987, just 3 years before Larson died. And so it's possible that the measurements are more accurate nowadays than they were 35 years ago, 37 years ago. The examples for discussion in this initial approach to the subject have been selected from among those in which these uncertain elements are at a minimum. First, let us look at element number 19, potassium. This element has a specific heat curve of the type identified by the notation n equals 3 in figure 4. That's in his chapter on specific heat. He identifies various elements by their n number, how many different segments of the curve, how many different line segments, because there are different transition points that an element will take as it heats up. And that's the specific heat, is like the efficiency of heat transfer. And as an atom heats up, it as heat is injected into the system, every atom will heat up at a different rate. But the atom will go through various machinations in order to avoid reaching the melting point, because statistically the solid state is more probable than the liquid state. And so the atom is going to do or the molecule is going to do everything that it can to avoid reaching the melting point. And so what it does is it grabs onto other rotational, again, remembering that the atom is made out of rotations of that initial progression. And so some atoms are able to make a few different transitions. Some are able to make no transitions. But in this case, potassium is able to make 3 transitions. Its thermal factors are 2, 1, 1, which is derived from those 3 initial numbers of the atom and the periodic table. For potassium, I believe potassium's numbers are 3, 2, 1, and it maintains the same factors throughout the entire solid range. As indicated in chapter 5, the endpoint temperature of this type of curve is 9.32 times the temperature of the first transition point. This leads us to an endpoint temperature of 336 degrees Kelvin. And the measured melting point is 337 degrees Kelvin. So in this case,